Good morning. My name is Brian Dutterer. I am the second lab instructor for MEGR 2156. Joe Dalton is also who you met in previous videos, and then Jeff Heacock, he will be our third instructor for the lab. We're all also available to help once you get through the lab and you're using machine shop tools throughout the shop to make your personal projects that you need for your classes. What today's lab is going to take care of is kind of an elementary operation on a lathe. So from here forward, we're going to be talking about two different types of machines. We've got lathe machines, also considered a turning machine, and then we've got milling machines. And the basic difference, the basic fundamental difference is that lathes actually hold the workpiece, rotate the workpiece. You saw a demonstration of that yesterday, and the tool is held stationary. Not always, but in most engine type lathes or lathes that you'll see in this machine shop, the spindle is horizontal, so parallel to the ground surface. You're going to hear a lot about orientations, axis orientations, axis callouts. You'll hear more about that as this series goes on. A milling machine, very similar to a drill press that you may be very familiar with, is it will actually take the tool, mount that in the spindle, and the tool rotates while the workpiece stays stationary. The operation that we're going to take care of today is called your facing operation. You likely heard that in a previous video. You are going to hear things over and over again. Some things duplicated, triplicated 4, 5, 6 times. You might hear these things. If you hear things multiple times, you need to make a mental note and say, that must be important to me. So you might want to write that down. There will be test questions that apply to this video series that you'll want to make sure that you understand. We also have what is called a safety test. So throughout the video series, while we're in the machine shop, you're going to hear myself and Joe and Jeff call out things and say, this item is on the safety test. It's going to be important that you remember it. So what I would do is write that down, because once you get through all of the explanation of the machines, you make the air engine, you get it tested, you get it released to the shop, you will not get access to the shop until you pass a safety test that we have generated that shows that you work safely in the shop. Because we don't want you to hurt yourself, and ultimately you don't want to hurt me, right? So you're going to see that as we move forward. That safety test is going to be very important to you. All right, so now what I want to do is I want to go over the contents of the gray toolbox. So when you check out your machine keys, you're also going to have underneath the key box, there'd be a series of different toolboxes, all with a number on them. So if you're on machine number 5, you're going to have toolbox number 5. So number 5 is going to be printed on the end of this toolbox. This is the number 1 toolbox. Okay? The contents that live inside of this toolbox are going to be your responsibility as you use the sophomore machines. If you open up the toolbox and you look at these tools and you say, I have no clue what any of these things are, until you get familiar with these tools, what you have to be concerned about is this little road map that lives up here taped to the lid of the toolbox. If I look in each compartment, and there's the proper number of tools. So in this upper left pocket, It says there's a number 2 center drill. Well, I don't have any clue what a center drill is, but there is a tool that lives in there. If I go through each one, there's a countersink, there's drill bits, taps, 2 plates, 5 different reamers. I can see that there's 5 plastic cases that house tools. And then over here is a die and a die handle. Again, if you don't know what these tools are, it's going to be important that you at least check. It's your responsibility to make sure that these tools are here. Does that mean that you're going to be financially responsible for these tools? The answer is no. If you see a tool that's missing, let your lab instructor or one of the shop managers, either Joe or myself, know that your tools are missing. We'll replace it so that the next person that comes through doesn't have to take the time to sort out those tools. Okay? So I want to kind of just take you through a once over of what these tools are so that visually you can look at them and say, okay, I know what a drill bit is. Most of you, and I would say most of you, because I do have some folks that have never had an opportunity in their life to be able to associate tools with their names, and all but one of these pockets inside this box are cutting tools. That one pocket we'll get to shortly. If you've ever used a drill bit in a drill press or maybe a hand drill that your dad or your granddad may have had, you're going to use a standard drill bit. So these are the types of drill bits that we have. All of the drill bits that we use are relatively short in length. Because they're short in length, we call those stub drills. They're actually used on screw machines and high production machines because they're very short, very stiff. I don't have to worry about their location moving around too much. Now the geometry of the drill bit is going to be important to you. If I can take my fingers, and yes, this is an extremely large drill bit, but we use this so it's easy for you to pick out the different points. Okay? I want you to be able to look at the features. So this is called the shank. The shank of the drill bit is what gets held in the drill chuck on either your drill press, your lathe chuck on the tailstock, or a chuck that lives in the spindle of a milling machine. That's just how you hold on to it. If I take this drill bit and I put my fingers in the smallest possible region inside of these grooves are called flutes. The main purpose of the flutes, there's actually a twofold purpose. Number one purpose, since this drill bit rotates clockwise, as chips are formed, it carries the chips up and out of the hole. You're going to have a much more efficient drilled hole if you're not cutting and recutting material. So we have to get those chips up and out of the way. Up here on this one, that flute is broken, but up here on this main cutting edge, this is called the cutting edge of the drill bit. Okay? The second purpose of these flutes, you can see that it's slightly angled, actually gives you a nice positive rake shear angle. We're going to learn more about that positive rake when we get to our lathe tools today. Okay? Again, we're going to be doing facing operations. We won't get into using the drill bits, but it's important that you understand the geometry. If I look at the end of the drill bit, there's a straight line. That straight line represents the web of the drill, that thinnest section. So if I've ever taken a hand drill and I try to drill a hole and I have a little X marked on my workpiece, and I start the spindle of the drill bit or the drill and it starts walking around. The reason that it starts walking around is because I don't have a specific center point that the drill rotates around. It's that whole web section. So if you think about geometry, a straight line is not a great way to start a hole on a very fine position that you have drawn on a part. So what we've done, or what industry has done over time, I'm going to make sure that you can see that. If you look at the tip of that drill bit, there is no straight line. You can see these back reliefs that are cut on, and it basically reduces that line to a sharp point. That's called a split point drill bit. So what a split point drill bit does is it allows me to go from a straight line to a point. So if I line the point of the drill bit up with the point of position that I want to drill the hole, it's going to be much more mechanically able to drill a hole at that exact position. I hope that makes sense to you. Okay? Now there are 7 different sizes of drill bits here. Okay, in talking about drill bits, I want to take your attention now to what's called the decimal equivalent chart. When you come into the machine shop, you're going to find different versions of this chart hanging at very specific spots around the machine shop. When I'm making parts, and I've been a machinist for close to 30 years now, when I'm making parts, I like to have everything that I need close to where I'm working, so that I don't have to go running all over the place to get information. Now if I look at the decimal equivalent chart, and if you haven't done very much in a machine shop or in a wood shop, you may think that the only size drill bits that exist are the fractional sizes. If you go to buy a small set of fractional size drill bits, they typically start at 1/16 of an inch. That's here. And they go all the way up to 1/2 of an inch. Okay? Now the reason this is called a decimal equivalent chart, and we'll start with the 1/2 inch because everybody knows what the decimal equivalent is for 1/2 is 0.5. Okay? But if I go back to the 1/16 diameter or 1/16 size, I can see that a 1/16 diameter for a drill bit measures 0.0625. Now from here forward, I'd like you to talk like a machinist talks, or like someone would talk in a machine shop. The base unit that we speak in is thousandths of an inch. So if I were to read 0.0625 as a base unit of a thousandths, I would call that 62.5 thousandths. Do I understand that? So if I take the decimal point and I move it over 3 places in theory, now I can call it 62.5 thousandths. Back to the 1/2 inch diameter, I would call my 1/2 inch diameter 500 thousandths. Okay? And I can go down through every different dimension. Now something that you'll see on this set of decimal equivalents is the English conversion, or the inch conversion, of metric sizes, and they jump in 1/2 millimeter increments. Okay, and you're going to see those highlighted in this light blue section. So all we really care about right now is what's in white on this specific chart. Okay, so if I went to Harbor Freight or one of the tool manufacturers and I wanted to buy, and we'll call it a complete set of drill bits up to 1/2 inch, what I would get is fractional that go from 1/16 through a half, and they would be in 1/64 inch increments, and a 1/64 of an inch is 15 thousandths and 6/10 of a thousandths. Okay, so that would be the increment that I would see those drill bits. Now that's one size, or one subset of the full set of drills. The next would be a numbered size. So a numbered size starts at 1, and on this chart it goes all the way to number 80. So a number 80 is 13.5 thousandths. Okay? You're not expected to remember all of these things. I just want to give you the basic idea. But in a full set that I would buy from a tool manufacturer, I would get number sizes from a number 1 all the way to a number 60. And a number 60 measures 40 thousandths in diameter if I'm talking about drill bits. Okay? The third subset that you would find inside of that set are letter sizes. And you can see here's an A. So the number actually starts at 228 thousandths, and goes down as the number gets bigger. The letter sizes start at A and go all the way to a letter Z at 413 thousandths. And they get larger as the letter progressively gets higher in the alphabet set. Now this set of drill bits would be 135 different pieces. So you would have 135 different sizes of drill bits in that set of drill bits. Okay? Now some of these sizes don't really have any specific reason, but as you get more advanced in manufacturing, you're going to find that a certain size drill bit may be a drill size for a clearance hole. It may be a drill size for a tap drill size hole. Okay? And we're going to talk some about different fasteners as this lab moves forward. It might be good for you, and I've worked on getting some small pocket decimal equivalent charts. They seem to be harder to get than what I had originally expected, but if I can get those, we'll be handing those out when you take the lab class. All right? But you can print the decimal equivalent chart off of an online website. So just pull up inch decimal equivalent, and you'll get all this printed out, and you can keep it in your notebook. Another section that I have set up, or I have not covered up here, are all of my different thread sizes. You're going to need to know different thread sizes as you move forward in design and manufacturing. Now basically what you're going to find out here is that a lot of these sizes, there's a lot of different sizes, but it doesn't cover every different size. Okay? There are special sizes that you'll run into in manufacturing. So in this chart, it starts at a 0-80. We're going to call that an 080 thread. Next is a 164 thread. And the 0, 1, 2, 3, 4, that represents the outside diameter. We'll get to that later on in this series. Once I get up above the numbered sizes, we get into fractional sizes. Some of these are really, really big. So a 1/4 is going to be the smallest major diameter screw that you run into in the inch sizes of screw threads. This second column is going to be your tap drill size. So just remember that set of terms there. So a tap drill size. That's going to be important as we move forward in this lab session. You can also print that off of an online website. What you'll realize is an 080, the major diameter of an 080 is very small. It actually measures 60 thousandths in diameter, so even smaller than a 1/16 diameter. Excuse me. Smaller than a 1/16 diameter, okay? And the biggest size on this chart is 2.5. Now you can get much larger than that, okay? So if I was screwing a propeller on a helicopter, I would want something way bigger than that because I don't want to fall out of the sky, okay? Now if you get into an industry where you're building helicopters, you're going to be using all different sizes in here, but likely nothing up here in this range. Now if I go into an industry where I'm designing and manufacturing hearing aids or watch components or cell phones, I may get into some of this, but I'm never going to see anything really this big, okay? So I want you to keep all of this stuff in mind, and a lot of this stuff we're going to go over multiple times throughout the lab session, okay? So now that we've went over this, I'd like to go back to the gray toolbox. All right, so now we're going to get back to the gray toolbox and its contents, because we want you to be able to at least start to recognize these tools. If I look at this center pocket, if I go by the road map up here, it says that I should have a 1/2 inch by 82 degree countersink, and there should be one. This is what's called a countersink. So it's got a shank. That shank is what gets held in the drill chuck. And then it's got the business end up here. This business end has multiple flutes on it. This one specifically has 6 flutes. And if I look at the angle, there's an included angle to this countersink. And the countersink that I'm holding in my hand has an 82 degree countersink. If you've not been in a machine shop before, you may sit and wonder, well, what in the world would I use an 82 degree countersink for? Even if you've not been in a machine shop, you've likely seen in household items, right, a flat-headed screw. So this is a flat-headed screw, and this is my thread, right? The end of the bolt is here. So if I wanted to fasten something down, say I have a plate down here, if I'm doing machining now, if I have a plate down here, I might want to drill a hole through, and then I would want to countersink, right? This is my section view here. I would want to countersink the top of the hole so that when I put this screw in, the top surface of the screw head becomes flush with the top surface of the plate. Now it's a much cleaner, a much more professional way to hide the head of a screw, okay? You're gonna see this included angle of 82 degrees on a lot of your standard hardware that you may pick up at Lowe's or Home Depot or some hardware store, okay? Most of these 82 degree headed screws, the flat headed screws that you find in the hardware store, are either going to have a straight bladed screwdriver slot in the top or a Phillips head, okay? Now once you get into more industrial type screws, they're going to be stronger. They'll give you a lot bigger variation of the threads that you may be able to use. Most of these screw heads, instead of having a Phillips or a straight head, are going to have a 6-sided or hexagonal, right, socket in the top of them. And we use what's called an Allen wrench. This is an Allen wrench. Allen wrench has a hex shape to it. They come in all different sizes. And you would use that to fasten down a flat-headed screw with a more industrial screw. Those screws go both in 82 and 90 degree heads on those. So if I was working for my boss says, we need to buy 5,000 screws because we're putting these covers on the face of these cabinets, I would want to make sure what size countersink or what angle countersink the parts were manufactured at. Because if you buy 82 degree head flat-headed screws to work on a cabinet cover that's got a 90 degree countersink in it, it's not going to hold as well or look as well as if you matched it. And if you did the design work, you're going to know the difference between the two. Okay? A lot of the bolts that we use are going to be driven in, especially when we're moving machines around, moving different components of machines around, a wrench. And this is just a standard wrench. It's got both an open end and a box end that has the same size. This is a 7/8 inch wrench. Okay? So the heads of those bolts will just be hex shaped, right? And then I'll put my wrench down across that to drive both tightening and loosening. Okay? There's another type of screw or fastener that you may use. This style fastener only has a hex-shaped socket in the top of it. So there'll be a pocket down in the top that's got this hex shape that we're going to use an Allen wrench for. Okay? This is called an Allen head cap screw. Okay? A lot of times you'll see on drawings they may call them out as AHCS. Allen head cap screw. Okay? Now in this instance, surely we aren't going to use a countersink to recess the head. We're going to use an end mill to recess the head. You don't know anything about end mills, but as we move forward in the lab, you'll learn more about them. Okay, so there's some of the fasteners that we're going to run into, and that's the reason for having the 82 degree countersink in this gray toolbox. Okay, so now we go to the next pocket. The next pocket has a center drill. The center drills that we purchased for the lab have a center drill cutting portion on both ends, so we get twice as much wear out of one tool. Okay, now these tools, the center drill, are used for starting holes. They're going to be very stiff, so when I put that in a drill chuck, it's going to be held very tight, very stiff to the drill chuck or the spindle of the machine, and you're not going to get a lot of floating around. So you're going to get a much more precise position of a hole if I use a center drill first. Okay? For mass production, we go back to that split point drill that we talked about earlier, because if I have 1,000 parts to make and I've got to center drill each hole, that takes a certain amount of time. If I can use a drill bit that takes the place of a center drill and still drills the hole, what does that do for me? Well, I'll tell you what it does for me. It allows me and my boss and my co-workers to make more money, because that's really what we're doing here, right? This is our job. So we want to try to cut pieces of the production sequence out so that we can produce more parts in the same amount of time. All right? So now if we move over to the second column, this top pocket has two tools in it. You can see that I've got two tools. There's one that lives inside of this orange box. But what these tools are called are taps. What a tap does is generates a screw thread on the inside of a hole. Okay? So if I was in the business of making machine screw nuts, I'd be really familiar with these things, okay? In one size of a tap, you may find that there's 10 different choices of a cutting tool from one manufacturer, one style tap, that gives you different thread limits. We're going to have a session of this video series that talks about threads and all the geometry that's involved in a thread. They're very complicated. So that cuts threads on the inside of a hole, very similar to way a machine screw nut would be. There's two different sizes because making the air engine, we use two different sizes of taps. We need threads of two different sizes. My next pocket down, second column over, closest pocket to me, has these crankshaft drilling plates. And yes, we use these to drill our crankshaft. It's that offset hole that allows the engine to have a throw to it or a stroke, okay? So we use these plates to hold that in our milling operation. Well, we're far away from doing any milling operations. So we're going to talk on that on a later lab. My next pocket is going to be reamers. Now I should have 5 different reamers. Now what is a reamer? I may not have any clue what a reamer is, so we're going to take one. I like to have a big one so that on this video you can actually see what's going on, so I'm going to pick that size. Now what I just did, and it's no magic trick, it's no sleight of hand, but what I just did is I took a reamer out of a plastic container and I threw the container back in there, right? That makes the most sense. Well, if I look at the sizes, the first size is 124 thousandths, second size is 126 thousandths. At this point in the game, you should start looking at that and you need to start relating size variations to some kind of how much difference is there. Well, between these two, a 124 and a 126, there's only 2 thousandths of size difference in those two reamers. 2 thousandths is roughly 2/3 the thickness of a standard sheet of notebook paper. A standard sheet of notebook paper that you would pull out of a loose leaf tablet, or I like going to the dollar store and buying the little tablet so I can take notes on them. All that stuff, and for the last 30 years, all that paper measures very close to 3 thousandths thickness, so I can use that as a reference. So if I have the ability to take a piece of paper and hold it up and look at its edge. Have you ever tried to do that? Well, before I was doing machining, I never did, but you can just barely see the edge of a sheet of notebook paper, okay? So that's 2/3 of that thickness. It's very small. So it's important as we start machining features with reamers that we measure that tool before we move forward, okay? So we're going to take our calipers and measure that. We'll get into that later on in this series, okay? Holding precision is what we're going to work with. Another thing I want you to remember is, because human beings have had their hands on these tools, if your case that your reamer lives in says that it's a specific size, now this box they've all been taken off of, this one says it's a 251 reamer. 251 is one of the sizes of reamers that I should have. There's no guarantee that that tool in there actually measures 251, because human beings have had their hands on these boxes and may have not put them back in the right container. So as we move forward, you're going to want to start measuring those. And we're going to go over that many, many times. Okay? So that's our reamers. What do reamers do? Well, after you drill a hole, if you want a nice clean finish, nice precise diameter, we're going to use a reamer. Because something that you may or may not know is if I take this drill bit and I drill a hole in a piece of sheet metal, and I'm sure some of you watching this video have seen that. How round is the hole that you just put in that piece of sheet metal? It's not very round. Well, if I drill it in a piece of wood, if I drill it in a piece of aluminum, I'm going to have the same problem. It may not be as well pronounced, but a drill bit typically drills a tri-lobed shaped hole. So it's got 3 lobes on it, okay? If I really require a nice round hole, that's what I'm going to use a reamer for. If I require a nice precise diameter hole, because if the drill bit doesn't drill a round hole, how can I expect for it to drill an on-size hole? It doesn't correlate. It doesn't work out that way. So reamers are used when there's 3 basic geometrical features that I care about for one specific hole. I want it to be round, right? I want it to be true to size, so my diameter is critical. And when I say critical, I'd like to have it better than a 1/2 thousandths to a thousandths from a nominal dimension. So if I reamed with a 251, the max deviation I might see is it may ream to a 252. But that all depends on how good of quality reamers you're going to purchase. And because we have lots of people use these reamers, we don't buy the best tools. We buy good, reliable tools, but we can't afford to buy the best quality tools. So we give you something in the middle, okay? The third thing that I care about, so I care about round hole, precise hole, and I care about a smooth finish on the inside of the hole, okay? They're the 3 features. If you were taking this class in person, I would stand there and say, you tell me what are the 3 features that I care about if I need to ream a hole. It's important that you remember those things, okay? Round hole, precise diameter hole, nice smooth finish on the inside. If you're not writing it down, you should be. The last column, the last pocket in this toolbox is a die and a die handle, okay? It says it's a 1032 round die. Well, if I look on the face of that die, this one's got a little oil on it, but I can look on the face and it says number 10, 32, NF. Well, NF stands for National Fine. So this is a fine thread. We're going to learn more about threads in an upcoming lab video. And I don't need to bore you with that information multiple times, but you're going to want to make sure you pay attention when we talk about threads, because there's lots of information that you need to grab. So what I care about in this box, a 1032 round die and a die handle. So that little die is a separate piece. If I loosen up these little screws, and they're called set screws, right? If I look at the side, there's a little set screw there. It's got an Allen head pocket in it for me to drive that screw. And I can loosen those screws. I can walk around this thing and I can see that there's 2 screws in this one. If I loosen those screws, this high-speed steel, oh, there's a buzzword, high-speed steel tap, or die, excuse me, that I can take out of this die handle, okay? High-speed steel, you should have heard that buzzword before, those 2 words before, because that's the material that we ground our lathe tool bit out of, okay? Starting next session, every time you come to the machine and you get your key it's going to be important that you grab the toolbox that's numbered to the same letter or the same number as what your machine is numbered to, okay? We keep that for record keeping purposes so that if there's tools missing, we can go back to that same person and say, Joe Smith, he's the guy that used the machine last. And remember, when you're done with these tools, put them back in the cabinet. When you're done with the machines, make sure that you put the keys back. And lastly, we're going to make sure that the machines are clean before you leave the lab. All right, so now we're done talking about the gray tackle boxes. You're going to want to get that gray tackle box starting lab number 4. In this lab, we don't actually use any of the tools out of the gray tackle box. It's just important that you know how to recognize those tools and what you're going to be responsible for. If I'm responsible for something, I want to know what I'm looking at, okay? So one thing that I want to start talking about now is the part drawing for the components that we're going to care about today, okay? One paper that's in your drawing set, and it's called out as sheet number 2 of 11. You should be familiar with that one because it's got your rough cut length on it, okay? That rough cut length, the only time we use the rough cut length in this class is in lab number 1, where we're hacksawing, bandsawing, or horizontal sawing of our work pieces, okay? So this drawing, or this piece, this cut sheet, or it's called a cut list, sheet number 2 of 11, we can set that to the side, okay? The parts that I care about today are going to be number 5, which is our stud, number 6, which is our piston, and number 11, which is our shaft, okay? The shaft is going to be the center of the crankshaft. It's what everything spins on. The stud is going to be the threaded stud, right, that the cylinder sits on, right? You talk about the motor, the air motor. It's this threaded stud up here at the top that the cylinder pivots back and forth on, okay? What I'm looking at now is sheet number 1 of 11. That just gives you a pictorial view of what the air engine looks like. Even though you've drawn the components, a lot of you folks aren't going to understand how the motor even works. Okay, so we want to develop that as our course goes along. All right? So the work piece that I'm going to care about first, we're just going to pick out item number 11. Item number 11 is going to be our shaft. Okay? That shaft, I can look at and I can start pulling dimensions off of that part drawing. So what I want you to have up in front of you is sheet number 11 of 11, and that's down at the bottom right corner. All right? I've actually taken the liberty of drawing up that part drawing, or most of it, on the whiteboard behind me. So if I start looking at this, I can start looking at the different features of the part. First thing that kind of catches my eye is this up here, my isometric view or pictorial view. Pictorial sounds very much like picture, and all it is a photograph or a picture of what that part or component looks like when it's finished. Okay? Again, all we're going to care about today is our facing operation. So we care about holding or maintaining the length. All right? You've been through a couple of lab sessions on this video series already. So you should understand some of the precision that we care about. Now when you're saw cutting a workpiece to length, We'll call that rough saw cutting, right? I don't care about the precision so much. If I can hold a 1/16 of an inch one way or the other, I'm golden. I don't have to control the size any better than a 1/16 of an inch. So that's 62.5 thousandths. We'll just say 60 thousandths just to make it easy on us, okay? From this point forward, our tolerances are going to get tighter. Now for us to expect that you can hold extremely tight tolerances right now, most of you have never even touched a lathe. I would be willing to bet 50% of you have probably not walked in front of a lathe. Okay? So what do I care about first? Alright, so we're going to get ready to start on this item number 11. The first thing I want to do is start looking at the drawing. So I have a paper drawing in front of me, but what I've done just for visual is actually copied some of the most important stuff that I want us to talk about on the board behind me. Remember, we're only looking at drawing number 11 currently, but for today's lesson, 5, 6, and 11 facing operations are all three very similar. So we only go over just the number 11 part. So you should have your sheet number 11 pulled out in front of you so that you can reference that. If you look at a part drawing, there are lots of different dimensions that you need to be concerned with. Besides dimensions, we also have to look at what the material is. Now on this drawing, the material says that it's drill rod. Well, drill rod is a steel. It's also a tool steel. The advantage to drill rod is the outside diameter of it is ground to a very high precision, and in a lot of cases polished after it's ground. That way the surface finish is very smooth. So because this particular component is the center of the crankshaft, I want it to run nice and smooth inside the main body of the air engine. Very similar to a car engine. You wouldn't take your car engine, pull the crankshaft out and beat it with a ball-peen hammer and put it back together and expect that it's going to perform the same. So we want to pay attention to the same things as we're manufacturing this very small engine, okay, for air motor. So all over this thing you're going to see dimensions. We're also looking at the isometric view. It just gives you a picture of what the final product is going to look like, called a pictorial view. So it sounds very much like a picture. Okay, a lot of times they use an isometric view for that up in the upper right corner. You're going to find down in the bottom that there's valuable information. One of the first things I try to look at is look to see whether the drawing is produced in first or third angle projection. So this is going to dictate how the component is rotated from one view to the next. Third angle projection is what we use here in the US. First angle projection is normally done overseas, and that is normally done in the metric system. Everything you're going to see in this lab is going to be in the inch dimensioning system. Okay? So these drawings that we use in the lab are all third angle projection, and you should have a good understanding of what third angle projection is. Once we get out of cylindrical parts, it's going to be easier for you to see how we go from the front view to the side view to the top view to the bottom view. And we'll go over that in the upcoming lab, okay? Another very important part that you're going to find is your tolerance block. Your tolerance block is down in the information region, right? In the title block of your part drawing. It's down in the box, down towards the bottom. Those dimensions are dictated depending on how many decimal places the dimension is. So if I look at this 1 inch dimension, The 1 is before the decimal point, but there's 2 zeros after the decimal point. So that is a 2-place decimal, okay? If I look down here, we've got 1, 2, and 3-place decimals determine what tolerance we need to hold that specific dimension. Now, if we kind of scan the drawing, we're going to see that the major diameter of the workpiece is called out differently. So its diameter, 187.5 thousandths in diameter, plus a 1/2 thousandths minus nothing. Well, the advantage is that tolerance is roughly 1/6 of the thickness of a sheet of paper. That's a pretty damn tight tolerance, okay? Well, why can't we go over and use the tolerance block dimension? Well, number one, the tolerance block dimension doesn't cover 4-place decimals. And if I see a specific tolerance tied to a dimension on the drawing, it actually overrides. So if I wanted to hold a tighter tolerance than plus or minus 10 thousandths on the overall length, I could draw that in on my part drawing and it would override my 2-place dimension, right, down here in the tolerance block. So this is the dimension that we want to care about. This tight tolerance already done for us. The drill rod that we saw cut it out of already holds that tolerance, so we don't have to be concerned about that. So what we are going to be concerned with is the overall length. What you're going to find with all the parts that we do is sometimes what we do is we split up different operations so that the class flows a little bit better. Okay? So we know we're going to use our drill rod because we see the drawing. On the drawing it tells us what material. We know that the overall length is at a 2-place decimal, right? That 2-place decimal tells me that I have to hold a tolerance of plus or minus 10 thousandths, which is over 3 thicknesses of a sheet of paper, which now we're getting into a tolerance that's pretty easy for most folks to be able to hold. It's a good way to kind of ease you in. Another thing that's on this drawing are these chamfers. The chamfers are called out 2, so there's 2 of them, 1 on each end. The dimension is 30 thousandths, right, by 45 degrees. We're not going to be concerned about cutting that today, but I want you to at least look at that dimension and know what the tolerance is. If I look at the tolerance block on this drawing, it tells me my angles, 45 degrees, have to be held within a 1/2 degree. I can tell you for a fact that they don't in this project. But we're going to show you how to precisely set up that angle so that you're at least close to that tolerance. It's going to be very difficult to be able to measure anyway because it's such a short dimension. But the 30 thousandths I'm allowed plus or minus 10. So that means my chamfer can be 10 thousandths bigger, or it could be 10 thousandths smaller. And we're talking about the legs of the triangle, not including the hypotenuse of the triangle. All right? So the 2 matching legs on a 45-degree triangle. You should understand that sort of stuff. So 30 thousandths, I'm allowed to be as big as 40 thousandths because I take 30 and I add an extra 10 to it. I can be as small as 20 thousandths because I take my nominal, which is 30 thousandths, and I'll subtract 10 thousandths from that, so I can be as small as a 20 thousandths chamfer. That's going to be pretty easy for us to hit as well. So the next thing we're going to go into is we're going to go into the actual setup. I'm going to do it on the whiteboard first. I'm going to show you the setup of a facing operation calculating RPM, which we've already talked a little bit about in one of Joe's previous videos. We're going to cover that again. Remember, things we go over multiple times are going to be things that you really need to understand. Okay? So we're going to go ahead and set up a drawing, just a quick drawing of how it's going to look on the machine. Talk to you a little bit about axes, and then we're going to move to the machine tool. All right. So now what I've drawn up here on the board is a drawing of our workpiece held into the machine by the 3-jaw chuck, and these are just simulations of what the chuck jaws would look like clamped on the outside of the workpiece. And then I've drawn our tool post, one of the tool holders. They're a dovetail block that your tool is going to be clamped into, and we use set screws to lock those down. And then this should look familiar to you, this piece of material that's clamped into my tooling block. It should be, or it is, your cutting tool, your lathe tool. This lathe tool is called a right-handed facing and turning tool. So there's two main operations that a facing and turning tool does, and if you were here, I would ask you, what are the two operations? Well, it's called a facing and turning tool, so it makes sense that it does facing operations, and it also does turning operations, right? The only thing on the tool that actually leaves the finish is going to be that small nose radius that you stoned on with the abrasive stone. That's what's going to leave the finish, okay? We stone that radius on there so that we can more aggressively have a feed across the part, because if we had a very sharp point and we fed across, you're going to get something that looks very similar to a record. It's going to be this sharp groove that you can run your finger across and have sharp edges. Those sharp edges are called burrs, B-U-R-R-S. We don't like burrs in this class, okay? So that means we're going to deburr the component after we do the facing operations. Again, facing and turning tool does those two operations. The only thing we're going to do today is our facing operation, okay? If I look at my workpiece, I can see that I have a certain amount of stick out. So the jaws grab a hold of a section of the workpiece. I have to be concerned about how much stick out, because if I have it stuck out 5 times the diameter in length, and it's clamped way back here, the workpiece is going to want to be flexible. Well, if it's flexible, it doesn't give me a very stiff operation, right? So I want to suck it back in, and I don't want this length overhang to be more than 2.5 times the diameter. Well, in this case, the diameter is 3/16 of an inch, right? So 2 times that is 3/8. Well, 3/8 is already approaching more than what I want to stick out, because this is a very short part to begin with, okay? So we want to be concerned about how much stick out. Another thing you're going to learn as we move forward, I know Joe talked to you a little bit about the structure and the mechanics of the lathe, but what I'd like to start talking to you about is the structure of the axes, okay? You're going to find out that there's nothing on the engine lathe that was designed or built by mistake. There's actually a purpose for everything that is machined and put together on a lathe. The things that I'd like to talk about right now are going to be the axes. So the Z-axis. That Z-axis is an axis or a straight line that's parallel to the center line of the spindle. You're going to hear that little stretch of words there several times during this lab session. The Z-axis is parallel to the center line of the spindle. Your x-axis is perpendicular to the center line of the spindle. So that being the case, your x and your z-axis are 90 degrees to one another. One thing I don't want to hear you say, once you get into my lab, is that the x and the z-axis are perfectly at 90 degrees, or exactly at 90 degrees to one another. The amount of money that you pay on a machine tool dictates how good the machine actually is. How much effort can someone afford to put into a machine that's only $5,000 a piece? Got lots of components coming together, you get to pay for all of it. If I spend $100,000 on a machine, they've got lots more flexibility on how much accuracy that they can build into it. Remember, a human being is responsible for getting these two axes 90 degrees to one another. And that 90 degrees also has to be in relationship to the center line of the spindle. If my z-axis is off and my x-axis is indicated good to the z-axis, they're both going to be off. Okay? So we want to be concerned about that. Once we look at those two axes, we have the ability to loosen this nut and rotate the tool relationship, right? So that it sits inside of that XZ axis imaginary lines or imaginary squares, so that the only thing that sticks out is the radius of the tool. So what we've done for simulation is we've taken this black magnet, right? This magnet actually looks very similar to your cutting tool. Now I'm certain when Joe went over grinding of the lathe tool, that one of the features of that lathe tool is that the leading edge, and I call this the leading edge because as I approach the material, it leads into the material. The leading edge and the front nose angle, so the angle between the front edge and the leading edge have to be less than 90 degrees. If you ground your tool to 87 degrees, that only gives you 3 degrees of rotational movement to get that tool set up. So if I loosen this nut, I can rotate it about that point, and this whole mechanism rotates. So I'm going to take that tool and I can rotate it in relationship to my axes, or more importantly, my workpiece, right? But it's how the axes interact with my workpiece. So I want to set it up so that if I have an imaginary square, this is my x-axis, and I take a straight line and I draw it down here, notice the only thing that comes in contact with that line is the radius of the tool. If I do the same with the z-axis, I draw a line parallel to the z-axis. As I move the tool forward, the only thing that comes in contact with that line is the nose radius. Okay? So what I'm going to do is I'm going to erase this tool post and my tool block. I'm going to take my magnetic tool and I'm going to position it, right? So that that 90 degree or less than 90 degree front nose angle fits inside this bottom right corner of, we can call it our Cartesian coordinate system, right? So I want to be able to rotate that tool around. If for some reason I have the tool sitting like this, it should be obvious to you that if I come up into the workpiece, there's a certain shape that I'm going to generate on the face of the part. Now that shape that I generate is going to be a cone shape. Nowhere on this drawing except for on the chamfer. Now all we're worried about is the facing operation. Nowhere on this drawing do I need the whole face of the part to be a cone. We'll take that back off. But if I orient the tool, again, why am I going over this so in depth? Because it's a hard thing for most people to understand. If I rotate this properly and I manipulate the tool and I drive it front to back in the x-axis, I can generate a flat, smooth surface on the face of the part. Okay? I want you folks to understand that. So that flat, smooth surface, the face of the part, is what I care about right now. Okay? So I've got my tool set up so that it's rotated properly. I'm going to take my wrench and I'll lock down the top of the tool post, that way it doesn't move, because there is a certain amount of cutting force that I need to be worried about putting onto that tool. I don't want it moving on me. So I'm going to take this tool, I'm going to bring it up close to the workpiece. You're going to see that in an on-machine demonstration here shortly. Okay? So if I bring this up, there's a couple things that I need to be worried about. Alright? I need to make sure my chuck is locked in. I'll show you how to do that with a chuck key, which is a different type of wrench that you'll need to become familiar with. We're going to lubricate the machine, because lubrication of the machine is also your responsibility as you come into the shop. And we need to make sure that the tool, if I'm looking at the top surface of the cutting, right, if I take a camera and I look down in straight from the top, that's what I'm looking at here. So it would make sense that the height of the tool makes a difference, right? If I don't have the height of the tool set just right, what it's going to do is cause me not to be able to reach the center point of rotation. So if I rotate the chuck, there is an exact center point of the rotation. I need you to understand that even if I'm running the chuck at 100,000 RPM, the center virtually isn't moving in theory, right? The closer to the center it gets, the slower it actually moves. The farther out to the outside, the higher your surface speed. All right, we're going to go into calculating our RPM here shortly. But I definitely need to make sure that the tip of the tool, what's going to cut, leave the finish, which is our nose radius, is vertically set up right. There's a trick that I can show you that's going to make your life a lot easier. All right? Now we're ready for doing some facing operations. Well, I'm definitely concerned about how fast am I going to run the spindle. Well, what are the things that I care about most? I care about what's the material that the tool's made out of. Well, we have two options. Those two options are high-speed steel and carbide. What we've gotten is we have a photocopy of a information sheet that you're going to find up in the front of our 2156 lab where all the machines are. This is going to be you'll have access to this every day you come into the shop. So as I was stating, you've got a couple of things you have to think about when you're calculating your spindle speed. The first thing that I want to be concerned about, and all we care about for now, is just this top section here. There's two columns, high-speed steel, HSS, right, or carbide. They're the two options that we have for cutting tools. They're the two most commonly used cutting tools in the shop. The next thing I need to be concerned about or determine is what's the material that I'm machining. Well, for starters, We use high-speed steel for everything, so we could get rid of this carbide. But there are times that we use carbide on hard-to-cut materials, so we leave that in here just for information. So everything we're going to do in the shop for this lab is going to be high-speed steel. The materials that we have to choose from, we have to decide what the material is. Now the material for drawing number 11, it actually is the same for drawings 5, 6, and 11. It's called drill rod. Well, I don't see drill rod on this list. What I do see on this list is annealed tool steel. So annealed tool steel is drill rod. The thing about drill rod is the outside diameter is cylindrical ground and in a lot of cases polished to a high precision on the outside diameter. So we care about annealed tool steel, high-speed steel, and if we bring those two together, we have a number of 50. Well, what does that 50 stand for? That 50 stands for surface feet per minute. So I want to think about that. Surface feet per minute. I want to kind of analyze what that is. If I were to take a 1-inch diameter workpiece, let's just pretend that this is our workpiece. This is 3/4 of an inch in diameter. I want to know how 50 surface feet per minute relates to a workpiece that's spinning in a lathe that the major diameter measures 3/4 of an inch. So 50 surface feet per minute. I want to run this fast enough so if I had some device and I could measure how much distance goes past one given point in a minute's time, I would need this to run fast enough that in a minute I have 50 linear feet of surface that goes past that point in a minute. Okay? So we can do a lot of things. We can calculate what's important. We can calculate what the circumference of a 3/4 of an inch in diameter is. And then we can convert our 50 surface feet per minute into inches so that they're like units, right? So the circumference would be in inches. We need the surface speed to be not surface feet per minute, but surface inches per minute. So we would multiply that surface feet by, that's right, a 12. So 50 times 12. Okay, and that would be 600 surface inches per minute. Now what I like to do is I like to round numbers, because what these numbers are basically good starting points. There's no window in space that says if you don't run at exactly 50 surface feet per minute that something's going to blow up or your tool's going to melt off and fall on the floor. This is just a good starting point. There are times, depending on the tool that I have, I may want to run faster, I may want to run slower. If I'm roughing material versus doing a nice fine finish, it might affect my spindle speed or surface speed of the workpiece moving. Okay? So if I do some rounding, that still gets me in the general ballpark, but I only like to round within about 10%. So at this point in the game, everybody should know what pi is. Everybody should know the value of pi within a couple of decimal points or decimal places. For reasons in this class, all I really care about is that you remember that the value of pi is 3. Yes, it's a little bit more than that, but again, we're just rounding. So we're going to simplify this down as simple as I can go, okay? instead of this being a 3/4 inch shaft, we're going to say it's a 1 inch shaft. So if I take a 1 inch diameter and I try to calculate the circumference of a 1 inch diameter, everybody should know what that equation is, right? Pi times the diameter. So again, we're going to round. So 3 times 1, which is 3. So on a 1 inch diameter, I can guesstimate that the outside diameter in circumference is roughly 3 inches. Well, now I'm going to take my 50 surface feet per minute, right? And we're going to turn that into surface inches per minute. So we're going to multiply by 12. So that's 50 times 12. And we can divide through, right? So 600 divided by 3. That's going to give us a good estimation of how fast we want to run the spindle, and we can set that up on the machine, right? So we're going to set that up on the machine, and we're going to say 600 divided by 3 is going to give us 200 RPM. Remember, this is a pretty big diameter, 1 inch diameter. Well, in our case, we've got the same material, right? So our annealed tool steel. But the diameter of our workpiece is 3/16 of an inch. So the decimal equivalent of 3/16 of an inch is 187.5 thousandths. All right? We're going to round that to 0.2 just to make things really, really easy for us. Okay? So we've got 0.2. If we take 50, we could easily divide our circumference, right? So it'd be 3 times 0.2, which is 0.6. And then 600, which is 50 times 12, which is 600 surface inches per minute, divided by 0.6, I get 1,000 RPM. So now we have our RPM. Well, that only applies to the exact outside diameter of the workpiece. As it gets in, the tooltip gets closer to the center of the workpiece, the spindle would have to increase. Well, on basic engine lathes, we don't have the ability to increase the spindle speed as we're facing towards the center. So worst case scenario, we're going to calculate to the outside diameter. That's the best we can do. If we were using a drill bit on a milling machine, we would calculate to the outside diameter. That would be worst case scenario. So that's basically if we use basic math and we understand circumference and that sort of thing. What we've done is we've taken that formula and we've diced it down so it makes things so easy that you can do it in your head. So we're going to multiply 4 times the cutting speed. My cutting speed up here is 50. So 4 times 50 is 200 divided by the diameter, which is 0.2. What's your answer? 1,000 RPM. See how simple that was? We're going to do that time and time again. Once you get into the machine shop and you're working with myself, Joe, or Jeff, and you come to me and say, "Excuse me, Mr. Brian, can you tell me how fast to run this?" We're going to take a field trip and we're going to go over and we're going to find this piece of paper. When we find this piece of paper, we're going to work back through those problems again, okay? So it would seem to make sense to me that this 4 times my cutting speed divided by the diameter should be written down in your notes. So we're back at the whiteboard. the last little clip before we go over to the machine so that you can actually see hardware moving around and actually metal cutting, okay? So we've got our tool rotated so that the only thing that's sticking out in both the X and the Z axis, what's going to give us the surface finish that we care about, is that honed nose radius, okay? We're going to start the machine up after we set our RPM with the handles on the front of the headstock. We're going to bring it over. A lot of times we can use the carriage to come over and touch the face of the workpiece. We want to do the touch off with the machine rotating. If we don't do the touch off with the machine rotating and the machine sitting still, it gives us a much higher chance to break the tip of the tool. If you break the tip of the tool, you get to take another field trip back over to the bench grinders, the pedestal grinders, and regrind the tip of your tool because it's not good for metal cutting anymore. So we're going to take our machine. We have to start the spindle. Well, I have two options. I have an option to run the spindle in clockwise rotation or counterclockwise rotation. Well, it makes a difference which way I look at that clockwise or counterclockwise rotation. So if I'm standing back here behind the headstock, I can see clockwise, counterclockwise. If I'm standing over here by the tailstock, counterclockwise is the same as clockwise on the other side. Clockwise is the same as, you get it, right? You understand? So if I come over here, this is the standard way that I'm going to look at rotation. Forward rotation, I want you to write this down. Forward rotation is clockwise from the motor end of the spindle. So I'm at the motor, looking down that way. Motor end of the spindle is clockwise. It's going to be similar to that in every machine tool that you ever run. Okay? And clockwise means that the material is coming down on the top of your tool. You ground a shear angle so that you have a positive rake angle that's going to allow the material to flow. Alright? So we've got our machine running. There's a lever on the side of the machine. We're going to push that down. I want you to understand that that pushing down motion is backwards to any machine that I've ever run in history. Normally, pulling it up gives you forward rotation. So I need you to make sure when you get on other machines, test that out before you get moving. Okay? So on these machines, pushing it down gives you a forward rotation or material rotating towards me, like so. Okay? Material's going down on the top surface of the tool. Alright? So we've got it wound up to something close to 1,000 RPM. Not always is the gearbox going to give you the exact RPM number that you've calculated. So we've got it set at something close to 1,000 RPM. We're going to bring the tool in. We're going to use the big carriage hand wheel. We're going to bring the tool in close, right? And then we're going to lock the carriage in. Because you're going to find out when we get up to the machines that the increment of accuracy, or the amount of accuracy that you can obtain from the dial on the carriage is much coarser than the dial on the compound. We have a compound setup. I'm going to show you how to get that dialed in. I believe Joe probably went over that on lab number 2. We're going to go over it again. So now I have this set up. My compound is here. There's a dial that sticks out and then a little hand wheel, right? There's a little split here and increments on that dial. Those increments, each one represents 1/1000th of an inch. Roughly 1/3 of the thickness of a sheet of notebook paper. So now that I've got my compound set, my compound is actually set up on these machines to be parallel to the Z-axis. Okay? So this line of axis and this one are both parallel. So that means they're parallel to the center line of the spindle. So I'm going to move the cross slide in. That's the other small hand wheel on the front of the carriage. I'm going to move it in this direction, Z negative, right? Z minus direction, until I just touch the material. As the machine's spinning, you're going to see little chips start to come off. As soon as it stops, as soon as it touches, you're going to back the tool off. Understand that this compound moves with the tool, but I'm going to just move the tool so I don't have to keep redrawing. Now that I have the tool tip in line with the face of the workpiece, I'm going to take this dial, and it's a slip ring. So if I hold stationary, I can dial it around so that it reads 0. So my 0 mark is up on top. Now that I'm off the part, I'm going to take this dial and move it in by 10 thousandths. 0.010. A little over 3 sheets of notebook paper. We're going to move it in. And as the spindle's running, now we're going to take some cutting oil. There's 2 different types of oils, lube and cutting oil. The cutting oil has a brush in it. That's the biggest way you can see the difference. I'm going to take that brush out, and I'm going to either brush it on the tip of the tool or on the end of the workpiece. Once I get some cutting oil on it, I'm going to slowly feed my cross slide in from the outside until the tangent point of the radius, that honed edge radius, is just past the center line. And then I'm going to feed back out. So I've taken one facing pass. So you should have some sort of a flat surface on the face of the part. You can give yourself a round of applause. You have finished one facing operation. Now we're not done yet. On week number 1, after you saw cut this with a hacksaw, you took it over to the belt sander and you chamfered the edge. You took the burrs off of the corner of that workpiece. So some of that corner, that ugliness, is still there. I want to take enough off the one end of that workpiece until all this ugliness goes away. Now we have roughly 1/8 of an inch over that we saw cut the piece. 1/8 of an inch is 125 thousandths. We're not going to go over that for sure. I'd like to do it in maybe 3 passes. So the next step, move in another 10, but I want to get rid of all that chamfer. And I'm going to feed in just past center, feed back out. Now if you shut the spindle off, you should notice that the end of your workpiece is getting even smoother yet. The whole surface should turn into a plane. Now since we've done a centering operation, this is a point where you can see, you can check and make sure that there's no center defect or center artifact because the tool wasn't centered properly. If it was not centered properly, we have to go back and recenter the tool. Remember, don't put your hands in here while the machine's running. So before I put my fingertip in there to see if there's a center defect or center artifact, I'm going to shut the spindle off. Take that lever and pull it back up. Let it coast to a stop. Now we're going to check it. Because we're all that good, we're going to say, okay, it's good enough. I've got a little bit of chamfer left, start the spindle, move in another 10 thousandths. If I need to put some more cutting oil on it, I can. I'm going to take my final facing pass, move over to the center, just past, back it back up. There should be a nice, clean faced end. Okay? Nice, clean faced end. Once we get this part done, you're going to be able to stop the spindle and take your finger across that edge, and you're going to feel a sharp edge. That sharp edge is called a burr. We need to deburr that corner. We're going to take a file, hold the handle in your left hand, support the other end of the file with your right, and you're going to deburr that corner. Now, deburring just means that I'm taking the burr off. It doesn't mean that I want to file a big radius on that corner. All it means is I want to take that burr off. I don't want to file a feature on the end of the part. I want to file enough just to get the burr off. Okay? So we should have a nice deburred edge when you put the file down. Okay? That's one end. Now I have to have two good surfaces to take a measurement. If you remember back, drawing number 11 tells us that we have to machine this workpiece to a 1-inch length. Now we know, because we understand tolerances now, that it can be as big as 1-inch 10 thousandths or as small as 990 thousandths. But our next step will be taking the part out, flipping it around, and facing the second end. So when I flip it around, that means I'm going to have a good end back here. I'm going to have a not so good end up here, right? So to save me from having to measure too much, I want to machine just enough off that I can take a measurement. It may not get rid of all that ugliness that you deburred on the end, but it does give you enough surface that you can take a good measurement, because you need two good parallel ends. So we're going to turn the part around, make sure the chuck key's locked in. Right? Clamped on the outside of the part. Start the spindle. We're going to bring the tool up and bring it in until it just touches. Once it touches, pull the tool back out. Set my dial to 0, right? My dial to 0. I'll show you how to do that on the machine. And we're going to move in 10 thousandths with this dial, 10 thousandths. Cutting oil. Face just past center, feed back. I should have, it might not be perfect, but I should have enough of a surface there to say I've got two parallel ends, right? As long as you didn't put a really big burr, we can go ahead and take the part out. When we take the part out, we're going to take our calipers. You learned about that on lab number 2. We're going to measure the length. You're going to see me do this on our demonstration portion. We're going to measure the length. And we're going to measure the length and subtract it. We're going to subtract the number that I'm shooting for. The number I'm shooting for is 1 inch. So if I get a measurement that's 1 inch 42 thousandths, how much do I have to take off? Right, I have 42 thousandths to come off. Remember, this end that's not really pretty yet, that's the end we want to take more material off. We're going to bring the tool up here after we get the part locked in with our chuck key, start the spindle, and we're going to come in nice and slow until it just touches the face of the part. Feed the cross slide back, right? Set my dial to 0. And from here, as long as I feel confident that my touch off didn't take off a lot of material, I'm going to take these cuts 10 thousandths at a time. So feed in 10, face past center, come back. Another 10, face past center, come back. The fourth pass will do 30, and then we'll just go to 42. 12 thousandths is plenty, is still a decent cut for us to make. Once I get to 42, I'm going to face past center, come back. I should have a good face. Right? What's the last thing I need to do? I like drawing these little guys here because folks understand that that little pigtail means that there's a burr on that corner. So I'm going to start the machine up. I can deburr at 1,000 RPM. Take the file handle in my left hand, support the end with my right. I'm going to take that burr off there. So they should go away, right? Should be a tiny little one. Remember, don't deburr so much that you've machined a feature on the end of your workpiece. Take your chuck key, loosen the chuck, take your workpiece out, double check the measurement for your overall length. Remember, we need to be between 990 and 1 inch 10 thousandths. If we are, we're good. We just did part number 11 for facing. We're going to do the same process with part number 5 and 6. Part number 6 is your piston. The piston has a diameter of 1/4 of an inch, where parts number 5 and 11 both have a diameter of 3/16 of an inch. So you're going to have to adjust your spindle speed. You need to know whether it's going to be a bit higher or a bit lower, and the answer is that your RPM is going to be a little bit lower. Not substantially, but if you're running too fast, well, most of us are going to be able to hear it, okay? Not so much on this, but other operations, if you're running off RPM, we know it before we get to the machine. So we've got this one done. You're going to repeat the same process for part number 5, part number 6. So now we've moved to the machine, and you should be at least a little bit familiar with engine style lathe. This is the chuck here. Been told about that a little bit. What I want you to understand is that the chuck isn't a part of the spindle that can't be removed. So if I need to use a larger chuck, or if I want to use a chuck that's got more jaws on it, I can actually take this chuck off. I can put a collet closure, which you'll learn more about collets later on in the semester's worth of videos that we're going to take. But as far as taking the chuck off, the first thing that you need to worry about is this. I need a block of wood, piece of plywood that we set on the ways of the machine, so that if the chuck were to come off and fall, it doesn't fall on the ways of the machine and damage the accurate component of the carriage operation. So we're going to put a block of wood on the ways of the machine. The next thing I want you to know about, I'm going to bring this pad of paper up here so that it's easier for you to see. On the back side of this chuck, at 3 locations, there's these square drives. Now it's a separate square drive from what we use the chuck key on to open and close the scroll of the chuck. But if I were to look really close at those square drives, I would see on this one, it's got a line an arrow and an arrow here. On the outside, on the black anodized or black oxide surface, there's a little tick mark. That little tick mark has to be lined up with this straight line in order for the studs to come out that hold the chuck on the spindle. Once we get it apart, it'll be easier for you to see. But this is also right here behind the chuck. And all three locations are the same. Okay? What this one means is clockwise to tighten, counterclockwise to loosen. So in 90%, 99% of the activities that we do in the shop, where you're tightening, you're going to tighten with a clockwise motion, and you're going to loosen with a counterclockwise motion. So I'm going to take my chuck key, and I'm going to rotate that square drive until that little line is lined up with that straight line on the body of the chuck. In all three locations. So there's the second one. There's the third one. So in this application, you can see that when I loosened all three of those drives, or those lugs, the chuck was kind of stuck on there. The reason it was stuck on there is because on the back side of the chuck, there's a tapered section. On the nose of the spindle, there's a male tapered section. So a female on the chuck, a male on the spindle. Those two are actually machined to be interference. The more quality the machine, the better interlock that it has. Now if the chuck gets stuck and you can't get it off, you can take a soft face mallet and just tap the top side of the chuck and it'll break those two tapers apart. Don't ever try to take a hammer very similar to what you would use to hammer a nail in to bang on the outside of the chuck, because now you're going to start changing the shape of the chuck. But a soft face mallet or a dead blow mallet would work just fine for that application. Now another thing that you notice when I take that chuck off is that there's metal chips back in that cavity. The metal chips get back in that cavity just from the metal cutting action. It's pretty normal. But what's not normal is that when you slide it back together, don't leave it dirty. Make sure that all of these interlocking faces and the mating surfaces all are clean and free of debris. Okay? So you're going to want to make sure that these surfaces are clean. If you recall from the beginning of this lab, or this lab video, I told you about the safety test. Just because it's my way of instruction, as I get along to something that may be on the safety test, I try to point it out to you so that it's highlighted, you can make notes of it, and then you really have no excuse at the end to pass that safety test. So mating surfaces being cleaned is mentioned several times in the safety test. The block of wood on the ways, mentioned in the safety test. Clockwise, counterclockwise, whether it's tightening or loosening, also mentioned in the safety test. So now that I have my chuck clean, those interlocking faces, you can see these pins have a little half circle cut out of them. So as I tighten those cams, because these are little cams, the square drives, it grabs a hold of this circular indent or this cylindrical indent and pulls the chuck back up into the face. Okay, that's important for you to know. If I rotate this spindle around, I can come up to a spot that has the number 0 stamped on it. Well, as I'm still novice to running this machine, I need to know what that little 0 stands for. So now we're going to get back to where we put the chuck back on. If I rotate this chuck around, you're also going to see another 0 stamped on the outside diameter of that chuck. I want the 0 and the 0 to line up. If I take and lift my chuck up, some of these chucks can be pretty heavy. I want to slide those 3 pins back in the holes. I make sure that my 0s are lined up, and one at a time I'm going to take that cam or the square drive and I'm going to turn that cam clockwise. Rotate to the next, turn the cam clockwise. Rotate it to the next, turn the cam clockwise. So now the second time I go around, there's only 3 of them. I'm going to put more torque on it, because the last thing that I want is that chuck coming off while the machine's running. Now we'll take the block of wood away. On our older machines, we would take the chucks on and off every day so that you became very confident and understanding how important it is to make sure that the chuck is secured on the machine. Because we have dedicated machines for this lab, we don't take the chucks on and off anymore, and it should keep us in a more safe environment. So when you come in, your chuck should be very well secured on the machine. Okay, so now we're going to go ahead and set up. Remember, we talked about this tool. You've ground one for your very own. This is called a right-handed facing and turning tool. Okay, so we're going to set that. Remember, this is in our tooling block. Again, I want to take and make sure all those surfaces are clean. Something that's on the safety test is the use of the airline. Please don't use it to blow yourself off or to horseplay with your friends. You can very safely check your surroundings, make sure that nobody's in the way, and you can use the air pressure. We have a little over 100 psi air pressure, and you can cause yourself some pretty damaging injuries if you're not careful, especially around your eyes. So these tool blocks have 4 set screws across the top. They have a thumb screw up here at the top that allows you to adjust that tool up and down like we spoke about at the whiteboard. I'm going to put my cutting tool in, and I'm going to make sure that it's kind of slid out and flush with this side of my tooling block, right? I want to make sure that how much stick out I have for the tip of the tool from the body of the tooling block. I'd like to limit that to below 2 or 2.5 times the square size. These are 3/8 square, 2 times is 3/4 of an inch. So if I can keep it from 3/4 of an inch and below from here to here, I'm satisfied. As many set screws as are engaged, I'm going to go ahead and lock those down. This is our Allen wrench, right? If I quickly want to turn it, I can use that orientation to quickly turn and get it seated. But to get a torque on it, I'm going to turn it so that I have more leverage, lever arm here, okay? That's going to torque it better in place. At a minimum, I'd like to have 2 set screws on my tool bit when I get ready to use it. If I want to lock that in position, I turn this handle clockwise. Notice that the tooling block doesn't go anywhere. If I turn it counterclockwise, I can move the block up and down, slide it out, manipulate it in my hand. Okay? We had spoke briefly during the whiteboard lecture time that I want to make sure that the orientation of the tool is correct. So I can take this 1-inch wrench, loosen the nut on the top, and now I have the ability to rotate the tool post 360 degrees if I want. But if I look at the top, remember my x-axis, my z-axis. I want to make sure that if I look at it on Cartesian coordinates, that the only thing that comes up and contacts that line, that invisible line, is the tip of the tool. Same thing in this direction. I want to make sure if I draw an imaginary z-axis line that the only thing that comes up and touches is the tip of the tool. That's what's going to give you the finish. Okay? I'm going to lock that down, and I'm going to let our camera come in and get a better view from the top to give you an idea of that orientation. Okay? So that pretty much takes care of setting up the tool. Remember, this is my cross slide. You're going to hear me reference that quite often. This is my carriage hand wheel. This is for coarse movement. And we spoke briefly about the accuracy of the carriage hand wheel isn't near what it is on the compound. This is my compound. One increment on my carriage hand wheel is 20 thousandths. One little increment or tick mark on my compound is 1 thousandths. So there's a 20 times more accurate dimensioning possibility here if we use our compound. So that's what we use during the lab session. If any of these hand wheels become extremely tight, it seems like it's taking you too much force to move the axes. Each one of those axes has a lock on it. This is our z-axis or our carriage lock. There's a cross slide lock back here that locks the cross slide. And then there's a compound lock. So if this compound lock isn't applied, it's not going to allow you to turn that hand wheel. Okay? So now that I have that set up, I have to worry about the vertical height of the lathe tool. So I'm going to take my workpiece. This is similar to the one that you folks did on week 1, lesson 1. I'm going to turn my chuck in, close it down smaller until my workpiece can get held in the center of those 3 chuck jaws. And if you recall, we wanted to keep it the distance of stick out. So the stick out is the distance between the face of the chuck jaws and the tip of the workpiece below 2.5 times the diameter. So this is 3/16. It's 187.5 thousandths times 2.5. We're just going to call that 0.5 because I like to round things. Okay? 200 thousandths is close to my diameter, times 2.5 is 500 thousandths. So as long as I stay under 1/2 inch, I'm satisfied. It's not going to be real flexible out here and causing me some problems. Now let's look at a trick that I can show you in centering the tool vertically. So I'm going to show you on something much larger. This is a round diameter, right? That runs concentric to the main spindle. So if I put my scale, this is a 6-inch scale. Joe's talked to you about that. If I put my scale and I put pressure on it, straight in, I can actually figure out where the center of the spindle is in a vertical orientation. So if I get to where my scale is perpendicular to the ground, I can feel pretty confident that I'm on center. So what I'm going to do here, you'll have to bear with me a little bit. I was in a motorcycle accident, lost my arm. So I put pressure between the tip of the tool and the diameter of the round stock. All right, so I have the tip of the tool pushed up against the round stock, but I've got my 6-inch scale pinched between those two. I'm looking for it to be perpendicular. Another trick that you can use, you take your combination square, set it up like this, and now we can set it on this flat surface of the cross slide. Remember, I said there's nothing on this machine that was made by mistake. So if I set it up, I can look at the relationship from a good square, it's not perfect, a good square, to where the center line of the tool is on how upright that scale is. Now it looks, from where I'm standing, that it was a little bit low. We're going to back the tool out. I'm going to make it extreme so that it's easy for you folks to see. So now I lowered it even more. You can see the extreme amount of tilt that that scale has, and it's leaned towards me. So that tells me that I have to raise the tool to get it on center. And I know that because I forced it low. So I'm going to loosen this post, right? My tool post. I'm going to turn that thumb screw clockwise. So what it's doing is lifting the tooling block. I'll lock it back down. So now that I have it locked, now I can repeat the process of pushing pressure. And I have to look again at how good and perpendicular the scale is in relationship to the ground or in relationship to this flat surface on the cross slide. So I'm going to take that scale out. It looks like I may have lifted it just a little bit too much. I'm going to back that screw off just a tiny bit. Just a tad more. The more effort you put in here, the better you get that parallelism that you want between the scale and the combination square, the better on center your tool is going to be. So once I get it centered, I can take my scale off and set it to the side. Before I'd ever start my spindle, I'd want to make sure that that combination square is out of the way. And now that I have positioned the tip of the tool close to the workpiece, I'm going to lock that carriage in place. So now, when I'm moving things around, I'm moving things in a very fine graduation, okay? Now I actually have my part drawings magneted up here to the back side, the chip deflector here on the back side of the machine, and we remember that the outside diameter is 3/16 of an inch or 187.5 thousandths. Remember, we're going to round that because we want to calculate our RPM. So recall that the formula is 4 times the cutting speed. The cutting speed for annealed tool steel is 50, so that's 200 divided by the diameter. I'm going to round 1875 to 0.2. Okay, so we're going to be 4 times 50, which is 200, divided by 0.2. It's going to give you 1,000 RPM. We're going to go over here to the headstock of the machine. If I have a choice, and I'm going to see that I have a choice here, these are the RPM choices that I have, right? So the closest that I can come is either 840, which is a little bit low, or 1050, which is a touch too high. But remember, these are just estimates. It gets you at a good starting point. Now, while you guys are just learning, if I had a choice, I would prefer to go to the lower number, okay? The lower number being 840. So 840 tells me that I need to be on black. See, I've got red, silver, and black here. And medium, low, high, medium. So I want to be on black. So if I push on this lever and I rotate my spindle, I can feel that I'm turning belts inside. If it feels like teeth of a gear are clanging together, it's not in gear, okay? So I feel comfortable that I'm in gear there. We're going to turn one hand wheel at a time. If you take both handles and you move them around, it's hard to tell which one's not in gear. Next, I'm going to take my low, high, medium handle. I'm going to pull on it. Now, as luck would have it, they slipped in really, really nice. There are going to be times that you have to fight a little bit to get this in gear. Don't get frustrated. If you got any questions, ask one of us and we'll come to you. So we've got the power turned on. I want to make sure that it's in gear. So before I turn the motor on and it starts clacking and thrashing gears up, let's just jog the spindle. If I hit this green button, I can jog the spindle. If it jogs and the spindle turns, that means that I'm in gear. If you get a bunch of grinding and thrashing, that means I've still got some work to do to get the RPM set up. So at 840 RPM currently, I'm actually ready to do some facing operations. Now at this point, you folks have already come in, gotten your machine set up, oiled with a lube oil all the positions that Joe spoke to you about in an earlier lab. If you have not done that yet, go ahead and take a second and make sure that happens. Okay? Once you get that done, there's a light on the machine. If you need more light so you can see what's going on, you can turn that light on. There's a cover that drops down. Okay? Just for ease of videotaping and filming, I'm going to pull as much back as possible so it's easy for our camera to come in and take a clearer shot. Now to get forward rotation, remember, what did I say forward rotation was? Forward rotation was clockwise from the motor end. So I'm standing back here on the motor end, clockwise, it's pushing material down on the top of the tool. So I'm going to start my machine up. If this machine running starts making you nervous, call one of us instructors over and we'll walk you through and show you that it's not going to bite you. Now you do have to give it some respect, because if you put your hands where they don't need to be, it can take and hurt you extremely bad, okay? But for right now, I'm going to position that tool so I come in and I touch the end of the workpiece. So if I move in nice and slow, now I can see some chips forming. I'll back the tool off. If you want a reference from 0, now would be a good time for you to rotate that 0 around so it reads 0 on the dial. Now as I'm rotating that around, notice this hand wheel's not turning. So what that means, see how it turned? If I'm turning the hand wheel, I'm adjusting where the tool is. Come up and touch again. Come up and touch. Material's cutting. I want to rotate that dial around until it reads 0, but not rotate the handle. Okay? We're going to feed in 10 thousandths or 10 little tick marks. Make sure our cutting oil is on the tip of the workpiece, and I'm going to feed slowly from one side just past center and then feed back. Okay? that's one facing cut. Now that it has stopped, I'm going to reach my fingernail in and see if there's a center artifact, and there is. Now the more comfortable you get with the machine, the more you're going to be able to feel whether it's too high or too low. And what I mean by that is that artifact shape is slightly different whether it's too high or too low. So if it's too low, it's going to have a really sharp edge to it. If it's too high, it's going to be more of a cone shape, and you're going to see that as time progresses. So all I did was loosen the tool post, adjusted the tool the direction I thought that it needed adjusted, and lock it back in. So now we're going to take another cut and check that center defect again. Start the spindle, move it in 10 thousandths. Make sure you have cutting oil. We're going to face to center, just past, and now back it back up. I'm going to shut the machine off. So now if I clean that edge off, put my fingernail across it, I don't feel any center defect. That's what we're looking for. Okay? I believe I said down on the whiteboard I want to take just enough off that bad surface goes away, where we use the belt sander to deburr the edges, and I want to make sure the entire end is nice and clean. I have a tiny bit more of sand of the belt sander edge there, so I'm going to take one more fine cut. Make sure that the machine has plenty of time to cut while you're feeding across. If you get what looks like a record on the end of the workpiece, you fed entirely too fast. Okay? So now I'm going to loosen that carriage because I've got the entire face clean. And if I take my fingernail and kind of scratch it over that corner, I can feel that there's a burr that's kicked up. Okay, that burr is bad. We don't like burrs. So we're going to take and deburr that corner. Now what did we say about deburring? We're going to use a file. I'm going to hold the handle in my left hand. I'm going to support the file end with my right hand. And I don't want to file so much that I cut a feature on the end of the piece. I just want to take that burr off of there. I'm going to show you a couple different ways that you can do this. But if I were to, you'll get used to my prosthetic hand. But if I do this, everything in the world on this machine that can possibly hurt me is between my hands and my chest. If I put the file handle in my left hand and I stand off here to the side, now everything that can hurt me is over there. So I'm not as vulnerable to the machine. So we're going to start the machine. As you get more comfortable, you'll be able to take your file, touch it on the corner, and then just roll it around the edge. What that does is files a nice little radius on the corner of the workpiece. Okay? Until you get comfortable, what you can do is start mostly flat, file, rotate, hit the edge, and rotate again, hit the edge. So instead of having a nice fluid motion, you're basically doing little flats. But regardless of which way you do it, the edge is now deburred. Okay, so now I haven't adjusted the height of the tool because I don't need to. That tool is attached to the mechanism of the moving axes. I'm going to loosen the chuck. Take that part out, right? I'm going to flip it around. I want to make sure that those chuck jaws are clean. If there are metal chips down between those chuck jaws, and I take the chuck and I squeeze in, those chips are the same metal as what the workpiece is. So what I'm doing is forcing chips into a nice polished surface. Again, I wouldn't take my engine, take the crankshaft out, beat it with a hammer, put it back in and expect it's going to run the same. We want to take good care of the outside diameter of these workpieces as we move forward. Now, even though I've taken the workpiece out, flipped it around and put it back in, none of this has to change. The only thing that's going to change is my zero on my compound axis, right? So I'm going to coarsely put the tip of the tool up. I'm going to lock my carriage in, right? The carriage being locked in is critical to holding the accuracies. Make sure nothing's in the way. There are these things called pinch points. It's on the safety test. What a pinch point is anywhere that you can stick your hand, right, or part of your body, that a moving component could pinch a body part. That's called a pinch point. We want to avoid them. If you open up a new manual for a brand new jet machine, it'll go over the pinch points inside the manual on the machine. Obviously, between the chuck and the ways here is a bad area. That's a pinch point. Any area that this cross slide can get pinched in something else and pinch your arm in, that's another pinch point. Okay? We're going to start the spindle. I'm going to bring the tool up until I just touch the face of the part. I'm going to back my cross slide off. Now I'm sitting pretty close to zero. So now I'm going to move in 10,000ths. A little bit of cutting oil. I'm going to feed to the center, just past the center, and then back. Okay? Notice I'm not touching the workpiece while it's still spinning. Now that I have a good surface, that gives me enough of a surface that I can measure. See, there's still a chamfer around that edge, but the surface is nice and smooth. So that gives me a second parallel surface that I can take a measurement. So I'm going to take my dial calipers. I want to make sure that the anvils are clean. A good way to know that is that my calipers go to zero each time. I'm going to open it up. I'm going to wipe my finger across the anvil of the calipers. There's my zero. Okay? Now I'm going to open my calipers up and I'm going to make a measurement across the two ends. Now you should be able to see that I'm still over an inch, and remember my nominal dimension that I'm shooting for is 1 inch. Well, if I read these calipers, I would read 1 inch. I'm not up to or past the 1 on the scale yet. So 1.0, 75 or 76, right? So that gives me 75 or 76 thousandths oversize. So that means I still have 75 or 76 thousandths to come off the length of the part. Feel free to use your air hose to clean out the mating surfaces or the touching surfaces, contact surfaces of the 3-jaw chuck. I'm going to lock my chuck down. I'm going to position my tool close to the face of the part, right? Lock my carriage in. Start the spindle. until I just touch. I'm going to set that dial to 0. So if I take 10,000ths cuts per pass, now on my roughing passes I can get a little bit more aggressive with my feed rate because that surface is going to get cut away with the next pass. So there's 40. 50. It actually goes pretty quickly. Put a little bit more cutting oil on it. 60. 70. And then one last pass at a little over 75 thousandths. Feed to the center and just pass, and then feed back out. I'll stop the spindle. I want to get the tool well out of the way so that when I do my deburring, I don't run into anything. We'll go ahead and deburr this in because once we measure it, we'll determine whether we're finished or not. I'm going to start nice and flat and roll the file around. I'm not putting a lot of pressure on it, just enough that it's in contact. Alright? And stop my spindle. I don't feel any sharp corners. I feel pretty good about taking the workpiece out of the chuck. Let's hold on to that. We're going to take a measurement across the length of the workpiece. Whoop. There we go. We're right at 1 inch. Now we're allowed plus or minus 10 thousandths tolerance, but we're right in the center of it. So we're not terribly concerned with the tolerance. We're within tolerance for sure. Okay? So that works you through the process of machining a facing operation to face item number 11 to length. So what is expected for lab number 3, which is the one that we're inside of right now, is machining to length for parts number 5, 6, and 11. Now we don't demonstrate all 3 because the process is the same. Just remember, when you get to item number 6, which is the piston, the major diameter of the workpiece changes. So that means my calculation for RPM is going to change. Okay? Make sure you hang on to that piece because you don't want to have to remake it. Now, the work that we've done today does not produce a lot of metal chips. But all the metal shavings that you see, the ones that you have been responsible for, is your responsibility to clean up. So what you can do, inside your brown toolbox, there's a brush for chips. You can take and brush all these chips down to the chip pan. There's a chip pan down below. Okay? Brush all these chips down below. There's blue towels that are hung all over the shop. We can grab a blue towel and wipe off the machine. I think it's important that we learn the good housekeeping for the lab. We can wipe down the machine, wipe down all the components. Make sure that you take your tool bit with you. If you do not take your tool bit out of the machine and take it with you, the next person that uses the machine may look at it as a bonus for them. They get a second tool bit that they can keep in their toolbox. Make sure you take that. If you lose it, you come back, or you left it here and we can't relocate it for you, it's going to be your responsibility to make sure that you can come on an off time and regrind another tool bit. Once you get all the chips brushed down, machine wiped down, this chip tray actually comes out, and you can take it to one of the trash cans around the shop with a blue towel, wipe it out, return your chip tray. The best way to make sure that the machine is clean enough, ask one of us lab instructors, and we will come by and inspect the machine and make sure that it's clean enough for you to get out of here. Okay, that is the completion of lab number 3, and here shortly I'll be starting lab number 4.